presentation, we have talked about perturbation theory. There are problems like hydrogen atom, rigid rotator, one-dimensional particle in a box, and harmonic oscillator are exactly solvable. By the way of solving the Schrodinger equation, we can get the exact energy eigenvalues and eigenfunctions. But most problems in quantum mechanics are not exactly solvable, and their solutions can be arrived at using approximation method. Perturbation theory is one of the approximation methods. If the potential energy of a system is disturbed a little and an exact solution is not possible. Now the system is said to be in a perturbed state. See this diagram. This is a one-dimensional particle in a box in the unperturbed state, whereas this is the same one-dimensional potential well with a disturbed state. So using the Schrodinger, by solving the Schrodinger equation, we can get the exact energy eigenvalues and eigenfunction of this problem. But whereas in this problem is concerned, we should go for approximation method. Now we have to talk about time independent perturbation theory for a non-degenerate case. First of all, we should know the difference between degenerate and non-degenerate case. See here, this is degenerate state, this is non-degenerate case. A system is said to be degenerate if two or more distinct eigenfunctions share the same energy. See, this is a single energy level, but two eigenfunctions psi1 and psi2 are sharing this single energy level. This is called our degenerate state. But if you think about a non-degenerate case, one energy level is shared by only one eigenfunction, E1 psi1, E2 psi2, E3 psi3. So the degeneracy is removed if you apply perturbation. The removal of degeneracy is possible with the help of perturbation. If perturbation is applied, the degenerate state is changed into non-degenerate state. So in this level, we should know about the term degeneracy. But in our discussion, we have to talk about non-degenerate case, time independent perturbation theory for a non-degenerate case. We know that the Schrodinger equation is Hsi equal to E psi. We employed the power series technique to expand H, and the extended version is H equal to H0 plus lambda H1 plus lambda square H2. Here H0 is our unperturbed Hamiltonian, H1 is our perturbed Hamiltonian. This is first order perturbation. H2 stands for the second order perturbation. Here the value of H0 is large. If you compare this H0 with H1, the given below are the eigenvalues and eigenfunctions of the unperturbed system. E1 0, E2 0, E3 0 and so on are the eigenvalues of the unperturbed system, whereas the eigenfunctions of the unperturbed system are psi1 0, psi2 0, psi3 0 and so on. Therefore, we may construct an eigenvalue equation for the unperturbed system H0 psi n 0 equal to En 0 psi n 0. This is called our unperturbed eigenvalue equation. Now the perturbed eigenvalue equation is H into psi n, which is equal to En into psi n. This is our perturbed eigenvalue equation. The value of En is En 0 plus lambda into En1 plus lambda square En2 and so on. The lambda is a parameter. 1 stands for first order energy correction. 2 stands for the second order energy correction. In the same manner, the wave function psi n is equal to psi n 0 plus lambda into psi n1 plus lambda square into psi n2 and so on. Here En 0 is a ground state energy level, psi n0 is the ground state eigenfunction. Now this is our perturbed eigenvalue equation. In this equation we have to substitute the value of h, en and psi n. Then the value of h is h0 plus lambda h1 plus lambda square h2. Then psi n is psi n0 lambda psi n1 plus lambda square psi n2, which is equal to, instead of en we have to substitute these values. Once again, instead of psi n we have to substitute these values. Then make our multiplication. h0 into psi n0 plus lambda h0 psi n1 plus lambda square h0 psi n2. Then take this lambda and then multiply with this psi n0. Lambda h1 psi n0, then lambda into lambda, lambda square h1 sine of 1. Then if you go for the higher order, neglect the lambda cube and lambda power 4 terms. Extend your multiplication up to lambda square. Then take this term lambda square h2 psi n0, this one. Then if you take your multiplication with this lambda psi n1, you can get lambda cube. No need to add this. Neglect the higher order terms. This lambda square into lambda square, lambda power 4. Neglect that term also because of the higher order. The right hand side also we have to make our multiplication in the same manner. Then we can get the equation of this form. Now align the constant term and then lambda term, lambda square term. Right hand side also the constant term en0 psi n0, then lambda term and lambda square term. You may get the equation of type 4. Now we have to compare the coefficient of each power of lambda. Say h0 psi n0 is available without lambda, which means that lambda power 0. Then here the right hand side is en0 psi n0 is a constant term. So h0 psi n0 equal to en0 psi n0. Now compare the coefficient of lambda, that is h0 psi n1 plus h1 psi n0 equal to en0 psi n1 plus en1 psi n0. Next compare the coefficient of lambda square, h power 0 psi n2 h1 psi n of 1 h2 psi n0, which is equal to en0 psi n2 plus en1 psi n of 1 en2 psi n0. So we may get three equations. Equation 5 is expressed in terms of a constant term, which is called as unperturbed eigenvalue equation. This is first order perturbation, this is second order perturbation. Now we have to evaluate the first order energy level, which means that evaluation of En1. En1 is the first order correction to the nth eigenvalue, and psi n1 is the first order correction to the nth eigenfunction. Here psi n1 is an unknown wave function. This unknown wave function psi n of 1 is expressed in terms of known wave function psi m0. For that, multiply psi m0 with a factor cnm of 1. So psi n1 is equal to cnm of 1 psi m0. Now the equation 6 becomes, say, take this equation, h0, instead of psi n1 we have to put this value cnm of 1 psi m0 plus h1 psi n0. This is h1 psi n0, which is equal to en0 psi n1. So en0, instead of psi n1 we have to put cnm of 1 into psi m0, then en of 1 into psi n0. This is en of 1 into psi n0. Now 6 is modified by way of substituting the value of psi n1. Here take the cnm of 1 as a first term, combine these two terms h0 psi m0 plus h1 psi n0, which is equal to Cnm of 1 into En0 psi m0 plus En1 psi n0. We know that H0 psi m0 is Em0 psi m0. From this logic, H0 psi m0 equal to En0 psi m0. Here H0 psi m0 is Em0 psi m0. So that instead of this term we can write Em0 psi m0. Here En0 psi m0 is available. Take the Cnm of 1 as a common term. Then this is modified as Em0 psi m0. Bring this term to the left hand side, that is taken as minus of Cnm of 1 En0 psi m0. If you take Cnm of 1 outside, then we can write Em0 minus En0 entire is multiplied by psi m0 plus H1 of psi n0, which is equal to this term En of 1 psi n0. Now multiplying equation 10 by psi n0 star and integrating, because our aim is to evaluate the value of En of 1, so that psi n0 is available here. If you multiply this equation 10 by psi n0 star and then integrate, we can get our normalization condition psi n0 star psi n0 d tau equal to 1. So Cnm of 1 Em0 minus En0, psi n0 star psi m0 d tau plus psi n0 star H1 psi n0 d tau, which is equal to, take this En1 outside because it is a energy term, then psi n0 star psi n0 d tau. Here this is our orthogonality condition. Psi m0 into psi n0 star. These two wave functions psi m0 and psi n0 are mutually orthogonal. Therefore, the product of one wave function with the complex conjugate of another one wave function should be vanished. So this is equal to 0. But here this is normalization condition. Psi n0 star, psi n0 d tau. Both the wave functions are in the same state. Psi n0, then the complex conjugate of psi n0 is psi n0 star. This value equal to 1. This is normalization condition. This is orthogonality condition. So this value is 0. This integral value is 1. So the entire is vanished. If it is 0, 0 into anything, 0. Then we may write this is 1. So En1 equal to psi n0 star H1 psi n0 d tau. In matrix representation we can write bra space of psi n0 H1 ket space of psi n0. En of 1 is equal to integral of psi n0 star H1 psi n0 d tau is represented in terms of matrix form as psi n0 in bra space, H1 psi n0 in ket space. Now the first order correction to the energy is the expectation value of the perturbation in the unperturbed state. You should know the meaning of this statement. The first order correction to the energy, En of 1 is first order energy correction term, that is expectation value. Expectation value is most probable value. If you do one experiment in so many trials, among the so many trials we can get only one particular value in most of the times. That value is called as most probable value or expectation value. Say En of 1, first order energy correction is the expectation value of perturbation. H1 is our perturbed Hamiltonian. Expectation value of perturbation in the unperturbed state, but the state vectors, which means that the eigen functions are in the unperturbed state. Psi n0 star, this is psi n0. These are all in the unperturbed state. The eigen functions are in the unperturbed state, but the total energy is in the perturbed state. So the first order energy correction is the expectation value of perturbation, that is perturbed Hamiltonian, in the unperturbed state. That's the meaning for this first order energy correction, En of 1. Now we have to evaluate the first order eigenfunction. For that, see here, En1 into psi n0, so that we have multiplied equation 10 by psi n0 star, because psi n0 star psi n0 d tau equal to 1, we can get En1. But our aim is we have to find out the value of Cnm of 1 in order to find out the first order eigenfunction psi n of 1 equal to Cnm of 1 into psi m 0. We have to calculate. For that, we should maintain this value of Cnm of 1. So, this is multiplied by psi m 0. Now, to evaluate the value of Cnm of 1, equation 10 is multiplied by psi m 0 star, because psi m 0 star psi m 0 d tau equal to 1. We may try to get the normalization condition. So, the multiply equation 10 on both sides by psi m 0 star. If you multiply, we can get Cnm of 1. See this equation. Cnm of 1 em 0 minus en 0 into psi m 0 star psi m 0 d tau. See here, psi m 0 star psi m 0 d tau plus the second term psi m 0 star h1 psi n 0 d tau. Psi m 0 star h1 psi n 0 d tau, which is equal to en1. Take this energy value outside, then psi m 0 star psi n 0 d tau. This is our normalization condition. Psi m 0 star psi m 0 d tau equal to 1. This is our orthogonality condition. This is in nth state, this is in mth state. So the value is 0. Therefore, we may write Cnm of 1 em 0 minus en 0 plus psi m 0 star h1 psi n 0 d tau is equal to 0. We cannot bring this term as 0 because this is perturbed term. This is perturbed Hamiltonian. But here we may take En of 1 outside and the remaining terms are combined, that will be leading to 0. But here we won't cancel this term. Psi m 0 star h1 psi n 0 d tau not equal to 0. But here psi m 0 star psi n 0 d tau equal to 0 because En1 is taken out as a number, as energy. But here this is an operator. So that this value is having some meaning, but here this is vanished. So Cnm of 1 em 0 minus en 0 plus psi m 0 star h1 psi n 0 d tau equal to 0. Therefore, Cnm of 1 is equal to minus of psi m 0 star h1 psi n 0 d tau whole divided by em 0 minus en 0. To change this negative sign as positive, then this em 0 minus en 0 is changed as en 0 minus em 0. If you write em 0 minus en 0 as en 0 minus em 0, this minus sign is changed as positive. But we may rewrite this term psi m 0 star h1 psi n 0 d tau in the matrix form as psi m 0 star is presented in bra space h1, this is h1, then the psi n 0 is written in ket space. We know the eigenfunction psi n of 1, which is equal to Cnm of 1 into psi m 0. Then the value of Cnm of 1 is psi m 0 star h1 psi n 0 d tau inside the integral whole divided by en 0 minus em 0. To change this negative sign into positive, em 0 minus en 0 is changed as en 0 minus em 0. Then this is the value of Cn of 1. Then this should be multiplied by psi m 0. This is the value of psi n of 1, which means that first order perturbed eigenfunction. Now we have to evaluate the second order energy correction En of 2. For that we should introduce the wave function psi n of 2, unknown wave function, in terms of known wave function psi m 0 by multiplying psi m 0 by a factor Cnm of 2. We know the equation 7, that is second order perturbation equation. In this equation we have to substitute the value of psi n of 2 as well as psi n of 1. Here also psi n of 2, psi n of 1. Now 7 takes a new form. H0 Cnm of 2 psi m 0 h1 Cnm of 1 psi m 0, then h2 psi n 0, which is equal to en 0 Cnm of 2 psi m 0 enm of 1 Cnm of 1 psi m 0 en of 2 psi n of 0. Now Cnm of 2 is taken as a common term. H0 psi m 0 is our em 0. Now here En0 psi m0 Cnm of 2 is available. Bring this term to the left hand side, so we can write Cnm of 2 into H0 em0 is em0 psi m0, then minus of em0 into psi m0. So Cnm of 2 into em0 minus en0 into psi m0. Just we have combined these two terms. This one and this one. These two terms are combined. But actually H0 psi m0 is em0 psi m0. So that Cnm of 2 em0 minus of, bring this term to the left hand side, minus en0, entire is multiplied by psi m0, which is equal to here Cnm of 1, this term Cnm of 1 psi m0, then minus of, this term is taken to the right hand side, Cnm of 1 h1 psi m0, then write down this term plus en2 psi m0. Here take out the Cnm of 1 outside as a common term, en1 minus h1 into psi m0 plus en2 psi m0. This is equation number 13. Now multiplying equation 13 by psi n0 star, because we have to evaluate the value of psi n, en of 2 into psi n0. So we have to create our normalization condition, that is our psi n0 star psi n0 d tau equal to 1. We have to arrive this condition because we need this en of 2 alone. Therefore multiply equation 13 by psi n0 star. Here Cnm of 2 em0 minus en0 integral psi n0 star psi m0 d tau, which is equal to Cn1 en of 1 minus h1 integral of psi n0 star psi m0 d tau plus en of 2 psi n0 star psi n0 d tau. This value equal to 1. This is a normalization condition. This is equal to 1. Here psi n0 star psi m0 into d tau, this value is 0 because this is our orthogonality condition. This is in mth state. This wave function is in mth state, but this wave function in the nth state. These two wave functions psi m and psi n are mutually orthogonal. So this integral value equal to 0. So the left hand side is 0. 0 equal to, say, minus Cnm of 1. Here Cnm of 1 into en1 into psi n0 star psi m0 d tau equal to 0. But minus h1, this is an operator, so we have to write minus Cnm psi n0 star h1. h1 should be introduced at the middle because we have to write this in matrix form. Psi n0 star h of 1 psi m0 d tau plus en2. Here we may separate this into two integrals. Cnm of 1 en1 into psi n0 star psi m0 d tau minus of psi n0 star h1 psi m0 into d tau. This factor not equal to 0 because this is an operator, Hamiltonian operator, plus en2. From this en2 is equal to Cnm of 1 psi n0 star h1 psi m0 d tau. We know the value of Cnm of 1, already we have evaluated this value. Substitute that values, then we can get en of 2 equal to psi m0 star h1 psi m0 d tau divided by en0 minus em0 into this term psi m0 star h1 psi m0 d tau. In matrix form we can write summation over m not equal to 1, then modulus square just psi m0 star h1 psi n0 into this term psi n0 star h1 psi m0 is expressed in terms of modulus of brass space. Inside the brass space we have introduced psi m h1 ket. Inside the ket space we can write our psi m. square. That means absolute square of psi m h1 psi n whole divided by En0 minus Em0. This is our second order energy correction term. In order to evaluate the second order eigenfunction, we have to multiply the equation 13 by psi m0 star and then integrate, because see the equation 13. In 13 we would like to calculate Cnm of 2. This is in psi m0. If you multiply by means of psi m0 star and then integrate psi m0 star psi m0 d tau, we can get our normalization condition. So this is equal to 1. So rest of the terms are present. So equation 13 is multiplied by psi m0 star, we may get the equation of this type. This is unity, normalization condition. Therefore Cnm of 2 Em0 minus En0 equal to Cnm of 1 En1 minus H1. This is our normalization condition, the value equal to 1. This is our orthogonality condition, this value equal to 0. This integral is vanished. This is our orthogonality condition, this value is 0. But this integral value equal to 1. This integral value equal to 1 because these are all normalization conditions. Then Cnm of 2 equal to Cnm of 1 En1 minus H1 whole divided by Em0 minus En0. Further we have to substitute the value of Cnm of 1. We can get to Cnm of 2. Now the second order eigenfunction sin of 2, which is equal to Cnm of 1, that is Cnm of 2 into psi m0. The Cnm of 2 is Cnm of 1 En of 1 minus H1 whole divided by Em0 minus En0. This is the value of Cnm of 2. Cnm of 2 is this much. Psi n2 equal to Cnm of 2 into psi m0. Then instead of Cnm of 2, we have written this value, entire is multiplied by Cm0. In this way, we have evaluated the values of En1, psi n1, E2, En2 and psi n2. That's all about our time independent perturbation theory for non-degenerate